Okay, I see a lot of people, a lot of familiar faces out here. So I'm going to talk about learning, and very quickly, what is learning? Can we do it? Can we do it well? And just to make sure that you're paying attention, 3 puzzles at the end. So for all of you who are in my machine learning class, you know, this is going to be all old hat. So good news. All right. You can each get a penny. We'll do an experiment afterwards. Okay. So I'll just tell you a little bit about learning, but very basic stuff, because you can go online and find out all the latest gimmicks and gizmos. Okay, and usually what you can do wrong when you have those complicated gimmicks and gizmos, you can also do wrong in very simple settings. So if we understand what you can do wrong in very simple settings, you're good to go. I guess the reason that I'm giving this talk is because data is everywhere. Okay, and so Netflix gave a $1 million prize for being able to process their data and make better movie recommendations. There's a current $3 million prize being offered by a health insurance company if you can predict how many days someone will stay in the hospital.
Some Arca students are participating in it.
Google, Amazon, essentially almost any online company these days, their entire business model revolves around data. Okay, so here's a simple question. And again, it's for those of you who are not in my machine learning class. Okay. What's the mathematical definition of a tree? So I'm going to ask, just pick one of you and ask you, what is a tree? Tell me what a tree is, mathematically. Okay. Anyone want to guess? Want to give it a shot? It's tough. Okay, give it a shot.
I can give you some properties of the tree.
But that's not a mathematical definition. That's just properties. So yes, that is the real challenge, is that, you know, you have to come up with a definition that says this is a tree, that's a tree, but this is not a tree. Okay, so, yeah.
That's
and I thought we were not in a CS class. Yes. So that's the CS data structure called a tree. We're getting even well beyond that.
So,
we're talking 3-year-old tree. This thing.
The computer science trees is always upside down.
Yeah.
This is all sitting upside.
Yeah. So you're talking about the root, the roots of a tree. But yes, the point is, it's very hard to mathematically define a tree. But if you take a picture of a tree to any 3-year-old, they'll look at it and say it's a tree. If you take a picture that doesn't contain any trees, they'll look at it and say it's not a tree. Okay? So somehow, even though you can take a 40-year-old and ask them what is a tree, it's very hard to pin it down. A 3-year-old has absolutely no problem. Okay? And what they've done is basically they've learned from data. That's essentially the power of learning from data, is that you can come up with solutions to problems, but not have a way of describing the solution to the problem. Okay. So, when can you use machine learning? Is when you know that there is some pattern. So there is something called a tree, and it's possible to distinguish between trees and non-trees. So if that's not the case, if it's not possible, there's no point using machine learning. And you don't know this mathematical definition, because if you did, you're done, go home. Okay? And you have data from which you can try to understand the pattern, whether it's how to distinguish a tree from not a tree, or, as we will see, there are 3 basic large paradigms of learning, and I'll just very quickly tell you 3 names. As far as you're concerned, they're just names. Okay, there's what's called supervised learning, that is it a tree or not? Okay. And that's related to the fact that if we're trying to learn if something's a tree or not, you give me labeled data. You give me pictures and you tell them, here are some pictures with trees, here are some pictures without trees. Okay. And here's another example where I give you some coins, okay, and I give you some coins which are pennies, dimes, nickels, quarters, and I tell you for all the quarters what's their size and their mass. Okay, what's there for all the nickels, the same thing, for all the pennies and for all the dimes. So you could imagine plotting every coin on a two-dimensional axis. Some of them are quarters, and so on and so forth. Different colors are different denominations. When you look at this, you might come up with some way of distinguishing between these guys. Okay? So you might place some lines and say, okay, if you measure the size and the mass and it falls in here, it's a dime. Okay? That's called supervised learning, where I give you data and I tell you for each piece of data what it is. Okay? There's an analog of supervised learning, which is unsupervised learning, where I remove the colors. I just give you data. This is mostly what goes on online, where you just have, for example, book data. Nobody's going to tell you this is a science fiction book and that's a mystery thriller and so on and so forth. You just have data. Okay. That's this example here. And you can imagine that there's still a lot of information. If you just looked at this, you could identify that, oh, there are sort of 4 different clusters or groups of data. And you could draw some lines and say, I don't know anything about this data. I don't know what these guys are that fit in here, but I know that they're different from everything else. That's just categorizing or organizing data. It's another way of learning from data. Okay, and then there's the way that most kids learn, which is, should I put my hand in the fire or not? Okay. And there's nobody out there telling you yes you should or no you shouldn't from which you can learn. And there's no real data except for your experience. So what you do, you put your hand in the fire. Okay, and then there's either pain or no pain. And on the basis of that, you remember next time you won't put your hand in the fire. That's also learning. Okay? And it's learning from the kind of data that's called experience. And that's a very good way of developing computer game playing algorithms. So without getting into details, if you wanted to build the world's best backgammon player, well, it was done using these kind of techniques automatically. So it's one of the few areas where machines have outwitted humans, which is backgammon. They're very good at backgammon. They're also very good at chess, but that's not learning. Anyone know how that's done? Chess, yeah.
Isn't it like just brute force testing of all possible?
Yeah, it's just searching the tree, yes, exactly. It's more like brute force tree search. Okay. So, you guys are the best learners out there. Okay, and if you were in my class, you've seen this. Okay, so I'm going to ask you to look at some data. So here's an example of data, okay, where I show you 3 patterns. And all those 3 patterns represent a tree. You might not think so, but they're trees. So f equals 1. Okay, f equals 1 is a tree. Everything on the bottom, you can view these as images. Oh, f equals -1, trees. And everything on the bottom are not trees. Okay, so take about 5 seconds to sort of look at this data. Apply your learning algorithms. Okay. Now tell me, what is this? Okay, so who says -1? 3 of you. -1. Okay. Who says +1? Most of you. Okay. So why +1? Yeah.
This sort of, I guess, feels symmetric in a
Okay.
sense.
Feels symmetric. So that's what you've learned. You've learned that, oh, the bottom is symmetric in some vague way, and the top guys look random. So who said -1? Yeah. Why -1? Top left. Yes. So if you look at the top left pixel in this image, it's black for all those guys and white for all these guys. Okay. So who's right? Okay, so this is the problem. Either of you could be right, either of you could be also wrong. Okay, and the point is that, okay, if I don't show you this guy, and you look at this, you think you've learned. For example, oh, symmetry, random. Or you think you've learned, oh, top left is white, top left is black. You think you've learned. Okay, but that's not learning. Okay, what learning is, okay, I showed you the data, you do whatever you need to do, and then I'm going to show you something you've never seen before. And if you can get that one right, you've learned. So learning has nothing to do with, oh, I understand the data. Learning has to do with, oh, if I see new data, I know what to do. And the problem here is that, in fact, in some sense, one can prove that, oh, there's nothing outside the data. You know, you could be right. It could be plus or minus 1. So in what sense is learning feasible? It's a somewhat of a dilemma, because all you see is the data, but you're interested in making predictions outside of the data. So you're interested in recommending a movie to me when I log into Netflix that I've never before seen. There's no point recommending to me the movie, you know, whatever it is, Flashback, or I don't watch movies, by the way. You know, which I've already seen and rated as a 4. Oh, you rated it as a 4? I'm going to recommend it to you. That's the data. The fact that I rated that movie as a 4. You want to recommend to me a movie I've never seen. You need to be outside the data. Okay? It's very hard. And that's the challenge. That's the real challenge in learning. Okay? So can we do it? So let's take a very simple problem. We just had the presidential election. Okay, and I'll show you a case where we can do it, and I'll show you a case where we cannot do it. Okay, so presidential election, people like to do what's called polling. So you stand outside, or you just randomly call up people, and you ask them, how did you vote? So you call up 10,000 people. Okay. Imagine that all people fit into a bin. There are the red people, Republicans, and the green people, Democrats. Okay. And you'd like to figure out what fraction of people voted for the Democrats. So what you do is you randomly pick a sample, okay, and in this sample there's more green, so you say, oh, there are more Democrats out there. Okay. Now ideally you would like to know the exact fraction, so you'd like to know everything that's going on in here, but it's not feasible. So what you do, you collect data. Okay, so this is all part of the learning process. You collect data, and then on the basis of this data, we would like to learn what fraction of green or what fraction of red is in the thing. Do you think this works, this process? There's one very important thing that makes this process work. The thing that makes this process work is if you picked your sample randomly. So this is when you can say, oh, in my sample, if it's big enough, okay, and I observe 35% Democrat in my sample, oh, 35% of the people are Democrats. It's very important that the sample is picked randomly, then you can learn. So, I'm not going to get into the details, but learning is hard because we need to make predictions outside the data. Learning is possible if you created your data in the right way. So, in what sense are we learning? Here's the sample, and 3/10 or whatever it is red. Okay. So far that's not learning because that's my data. But when I make the prediction that 3/10 in the bin is red, I'm going outside the data. That's why it's learning. But it's a very simple case of learning. It looks much simpler than this. It turns out that they're very similar. Okay. Let's show you another example of learning. Imagine that you're trying to learn a function. So this is another example of learning. And I give you data points, blue data points. What would you do in this situation? You're trying to learn this blue function. You don't get to see the blue function. You only get to see the blue data, the red data, the black data. What would you do? So this is what sort of, if you're a statistician, this is what you would do. You would say, oh, you gave me 5 data points, let me fit it with some kind of a curve. Okay. So, do you think that we could fit it with a line? Probably not. Okay. Can we fit it with a parabola? Well, this blue curve is a parabola, but we cannot exactly fit the data points with a parabola. What type of curve would we need to fit the data? Anyone know?
Fifth order?
Fifth, maybe fourth order. Okay. A fourth order polynomial would guarantee that we can fit the data. Okay. And now I'll show you why that's a problem. And that's the difference between inside the data and outside the data. Okay. If you guarantee that you fit the data, you think you've learned. So let me fit a fourth order polynomial to this data. That's the result, the red curve. Does anyone here think we've learned? Probably not. Okay. This would be the output. But It fits every data point exactly. So here's the obvious thing I did wrong. I picked the wrong fourth order polynomial. Can someone tell me why I'm talking nonsense?
Isn't there only one
Yeah,
of an order?
I didn't pick the wrong one. It's unique. There's only one fourth order polynomial that fits these 5 points. So it's not even that I picked the wrong one. There's some very subtle problem here. So looks like the data quite reasonably represents this